In the last few classes, we were discussing about the perturbation theory, Feynman diagram, and Feynman rules. So let's recall the interacting theory endpoint function. So in interacting theory, the endpoint function is given by Gn x1 up to xn is equal to the interacting vacuum time ordering of the fields phi of x1 up to phi of xn. In terms of the free scalar field theory, I can write this as time ordering of x bar e raised to I si divided by time ordering of e raised to I si. So here the phi of x1 up to phi of xn is actually represented by x bar, and si represents the interacting action, that is the action for interacting theory. After expanding the power series, we can write the numerator and the denominator for mth order perturbation. If the perturbation is of mth order, then I can expand the numerator and the denominator as follows. So I raised to m by m factorial time ordering of x bar. Okay, so after expanding, there will be m times si. Okay, m number of times. Now divided by, in denominator, we have I raised to m by m factorial time ordering of si's. Okay, there will be m number of them. So this can be computed using Wick's theorem, but we go for Feynman diagram and analytical expressions. Any diagram contributing to the numerator of the endpoint function has n external legs with m vertices, and the diagram corresponding to the denominator have no external legs as there are no phi present there. Okay, and therefore they are called as the vacuum diagrams. Now the denominator can be used to calculate the vacuum energy of the interacting theory, and therefore in this class we focus on the computation of this numerator and denominator involving two basic steps. So the computation involves two basic steps, and the first step is to draw all equivalent Feynman diagrams. Okay, so here we have x1, x2 up to xn. There are n points, right? There are n external points. And since this is an mth order perturbation theory, we have m vertices. We have m vertices because we are considering mth order perturbation. So this m vertices can be represented by y1, y2, etc. up to ym. Okay, and there will be 4 legs in each vertices because we are considering the interacting theory. Si is equal to integral lambda by 4 factorial phi raised to 4d4x. Okay, so we are considering 5 raised to 4. Therefore, there will be 4 legs in one vertex. So this is all about the numerator of the above expression, right? In the denominator, there is no phi present, right? Here you have seen that there is no phi in the denominator, and therefore it will be a vacuum diagram. Okay, diagram corresponding to the denominator have no external legs, and there as there are no phi's, and therefore they are called as a vacuum diagram. And these vacuum diagrams, we have seen already that they are closed. They are always closed, and all the legs will be contracted. All legs will be contracted. Okay, and therefore they are also called as vacuum bubbles. So this is all about the denominator of the above expression. Okay, so the first step in computing the endpoint function is to draw all equivalent Feynman diagram. Okay, so which can be done in this way. Then the second step is to convert the diagram, convert the diagram into algebraic expression. This can be done using the Feynman rules, and after that you have to sum it all over. So we can convert the diagram into algebraic expression using Feynman rules, okay, that we have seen in the previous class, and then so you can sum it all over. This is the second step. So the third step is to do all the integrals. One thing you have to be careful while doing this integral is that the action in the interaction theory, SI, can contain multiple terms leading to multiple type of vertices, diagrams, etc., and they can get complicated. Okay, so you have to be very careful, as SI may contain multiple terms involving the phi, leading to multiple type of vertices. And the diagrams get complicated. And if there are multiple fields, each field propagators are represented by a different line. For example, if you have two scalar fields phi1 and phi2, then the action for the interaction will be proportional to integral d4x phi1 square phi2 square. Then the propagator can be represented as phi1 and phi2. Okay, so the vertex will be something like this, right? So it will involve both the fields phi1 and phi2. If there are multiple fields, each field propagators are represented by a different line. Okay, the endpoint function in the momentum space is given by 2 pi to the power 4, 2 pi to the power 4 Dirac delta P1 Pn, Gn, P1 up to Pn. Okay, so this is the Fourier transform of the endpoint function in the coordinate space. And here you can see that the P1 up to Pn, they are arbitrary. So no need to satisfy the on-shell condition. They are arbitrary. Now we are ready to calculate the endpoint function. Okay. So there are two steps in the computation of the endpoint function. The first step is to draw all the equivalent Feynman diagram. Second step is to convert the diagram into the algebraic expression and then sum it all over, and then final step is to do the integration. And you have to take care of certain things involved in the Feynman diagram. And after that, now we are ready to evaluate the endpoint function. For simplicity, we start with two-point function. So the two-point function g2 x1 x2 can be represented in terms of the Feynman diagram as the lowest order plus bringing down one interacting term plus higher order perturbation divided by 1 plus higher terms. So this is the lowest order, and this is when you do bring down one interacting SI. Okay, from the exponential term, when I bring down one interacting action, then you get this diagram. Okay, now I do the binomial expansion to the denominator. Okay, now I do the binomial expansion to the denominator, and then I'll get the lowest order plus the straight propagator times the vacuum bubble minus straight propagator times vacuum bubble plus other higher order perturbation. Okay, now here you can see that these two will get cancelled. Okay, and this cancellation is not by an accident, and it happens in all order. So this is in the first order, similarly in the second order and the third order, and in all the order this happens. Okay, we have already seen this in the previous lectures as well. Now the numerator of the endpoint function, if I represent it by un, then it is a sum over all the Feynman diagrams with n external legs. So sum over all the Feynman diagram with n external legs, because we will have n external points. So n external legs. Then if I represent the denominator by u0, if I represent the denominator by u0, then it is sum over all the Feynman diagrams with 0 external legs. Then the endpoint function can be written as un by u0, and this is the sum over all the diagrams with n external legs but without any vacuum bubbles. So that's what we have seen here. Once you divide it with u0, right? Once you divide it with u0, then you will get sum over all the Feynman diagrams, but you have to remove all the vacuum bubbles. So un by u0 is the sum over all diagrams with n external legs but without any vacuum bubble. So this without is very important. It's without any vacuum bubbles. If you go to the next order, then you'll get something like the straight propagator multiplied by the vacuum bubble. Okay, and this will automatically cancel and the expression will get simple. What is the physical interpretation of this cancellation? The vacuum bubble comes from normalization of the states, which is a pure vacuum process. So once you normalize your state, they will not contribute to correlation function. So that is the physical interpretation. Okay. So vacuum bubble comes from the normalization of states. Okay, which is a pure vacuum process. And once you normalize your state, they will not contribute to correlation function. And that's how the vacuum bubble get cancelled. So you can write the 2-point function, okay, for higher orders as something like this, plus, right? This is up to second order. Okay, so this is up to second order. And similarly, the 4-point function can be written as, so initially there is no interaction. So in 4-point function, no interactions can be represented like this. Okay, so these are all no interaction or the 0th order perturbation plus, okay, the first order interaction will be like this, etc. Right? So I can have terms having something like this, right? Like this. Then you can also have something like this, right? And you can also have terms like this. Okay. So one thing that you have to note is that the endpoint function, total endpoint function, is actually the sum of the connected diagrams. Okay, connected diagrams plus the disconnected diagrams. So what are connected and disconnected diagrams? If you see here, this is a connected diagram. Then this is also a connected diagram. So what is a connected diagram? If the diagram has all the external legs are connected within a single diagram. Okay, if all the external legs are connected within a single diagram. All the external legs are connected within a single diagram. So this is also a connected diagram. Right? But this is a disconnected diagram. So this is a disconnected diagram. So what is a disconnected diagram? The external legs separate into product of subdiagrams. The external legs separate into product of subdiagrams. Okay, and this is also a connected diagram. So we can say that the endpoint function can be written as the sum of connected diagrams plus the disconnected diagrams. Okay, so that is the first thing that you have to note. Now, all the external points can be associated with the momentum. That can be anything in general. So till now, we have not put any constraint on the type of momentum that the particles can have. So all the external points can be associated with the momentum that can be anything in general. But we have seen that the LSC theorem tells us how to obtain scattering amplitude from time ordering correlation function. Right? That is, if you have the endpoint function in the momentum space, and suppose if all the pi are on shell, right? If all the pi are on shell, then there is a condition pi square must be equal to minus m square. So this is known as the on shell condition. So pi0 will be equal to plus or minus omega pi, right? Because there are two roots, positive root and negative roots, and omega pi is root of m square plus pi square. So we can divide the momentum into two categories. First one is p1, p2, etc. up to pm, and the next category is from pm plus 1, pm plus 2, etc. up to pn. Okay, the first category I can represent it by p alpha 0 is equal to minus omega p alpha, that is the negative roots, where alpha is equal to 1, 2, 3 up to m. And the second category is represented by p beta of 0 is equal to minus omega p beta. Okay, sorry, here it will be plus omega p beta, that is the positive roots, where beta is equal to m plus 1, m plus 2 up to n. Okay, so the LSC theorem, under the on shell limit, we get 2 pi to the power 4 Dirac delta p1 plus p2 up to pn gn p1 up to pn will be the product of all I equal to 1 to n, and there is a constant here which I'll be representing by root z. So this is a constant by pi square plus m square minus I epsilon multiplied by this term pm plus 1 up to pn comma plus infinity, then p1 minus p1 up to minus pm minus infinity. Okay, and this term, this convolution is the scattering amplitude. This is known as the scattering amplitude for particles with initial momentum minus p1 up to minus pm, okay, at time t equal to minus infinity, transitioning into the particles, transitioning into particles with final momentum pm plus 1 to pn at time t is equal to plus infinity. Okay, so which means that this is equal to 2 pi to the power 4. Okay, so this is the scattering amplitude, which will be 2 pi to the power 4 Dirac delta p1 up to pn m alpha beta. Okay, now if you see the LHS, there is a 2 pi to the power 4 and Dirac delta, and on the RHS I have a 2 pi to the power 4 Dirac delta. So both will cancel from each side, and finally I can write the endpoint function Gn is equal to the product of I, right, root z by pi square plus m square minus I epsilon m alpha beta. Okay, so you can see that these are propagators. These are propagators for external legs, right, and this is the transition amplitude. To obtain the scattering amplitude m alpha beta, first you have to take the endpoint function. So take the endpoint function, and then you have to take all the pi's on shell, right? What do you mean by on shell? Initial momentum with negative roots and final momentum with positive roots, and then truncate all the external propagators. Truncate all the external propagators. So if you take Gn and then put all the pi on shell, and then if you truncate the external legs, then you will get the transition amplitude. So in essence, the scattering amplitude is equal to sum over all the truncated diagrams with external momenta on shell, right? So in summary, I can write the scattering amplitude is the sum over all truncated diagrams with external momenta on shell. Okay, so for example, we can consider the 4-particle scattering. So when you have a 4-particle scattering, then you have minus P1 minus P2, which scatters into P3 and P4. So this can be represented by G4 truncated P1, P2, P3 up to P4. And here you have to see P1 and P2 are minus omega P and P3, P4 are, they have plus omega P roots. So P1 and P2 have negative omega P, which means minus P1 and minus P2 will have positive energy. Okay, so that is sorted out. Okay, so now in these diagrams, if you consider, then these are all with no interaction, and the leading order interaction term is something like this. So the leading order interaction for the 4-particle scattering will be, right, minus P1 minus P2 P3 P4 plus the other higher order terms. Okay, so this is the leading order interaction. Okay, now from the Feynman rules, you can see that this diagram contributes to, this is a vertex which contributes to minus I lambda, right, plus the other higher order terms. Now to calculate the Green's function, you have to calculate the propagators, but we have to truncate the external propagators. Fine. Now second example is something called as the decay of a particle into 3 other particles. Okay, so you have a particle which decays into 3 particles. So minus P1, P2, P3 and P4. So similarly, you can write a 4-point function, right? Then here P1 will be minus omega and P2, P3, P4 will have positive roots. And in the similar way, you can write the leading order diagram minus P1, P2, P3, P4, right? And in the same way, you will also get a minus I lambda from the vertex plus the other terms. Now I have some remarks to make, okay, which is regarding the disconnected diagram. The disconnected diagrams factorize into subscattering process of lower orders. For example, this is a disconnected diagram, right? This is a disconnected diagram. Now this is actually factorized into subscattering processes. Okay, so it's a multiple of some subscattering processes of lower order. So this can be represented minus P1 to P3 and minus P2 P4, right? Sorry, here it will be plus P3. So P1 to P3 and P minus P2 to P4. So they factorize into subscattering process of lower orders. I can give you another example as well. If you have three particles interacting and scattered into three other particles, okay, then it can be represented by two particles coming together and scattering multiplied by single particle scattering. So there are factors. The subscattering process are factorized and each of them are of lower order, right? But we are interested in processes involving all participating particles. Okay, so we are interested in processes involving all participating particles. All participating particles. Okay, so we do not consider disconnected diagrams. We are not interested in disconnected diagrams. And another point that I want to highlight is that you have a diagram which is like this. Okay, and this diagram is not different from the vertex which is like this. So there is no difference between these two diagrams. No difference between these two diagrams. Both of them are vertex. Okay, and why there are no difference, but you can say that there is an interaction here, but after truncating the external propagators, then these two diagrams have no difference. Fine, so we already talked about truncating the external propagator. So once you truncate this external propagator, then this will be equal to this interacting vertex, right? And therefore this diagram do not contribute to the endpoint function or the scattering. This diagram do not contribute to the scattering amplitude. Okay, so anything happening to external legs can be ignored. And if that is the case, then the scattering amplitude m alpha to beta can be summarized as the sum over all truncated, right? Because we are truncating the external legs, then connected, because we do not consider disconnected diagram, we consider only connected diagrams with all particles participating in the scattering process, and on shell diagrams because we consider all the momentums to be on shell. Therefore m alpha beta is equal to sum over all truncated, connected and on shell diagram. Okay, so for this class we stop here.